Now, outside of the actual main topic here of this workshop here, but I thought it might be interesting to look at actually what we mentioned here, some of the co-workers here, some PhD that's from Dash actually PhD doing PhD right now here at KDH. This is a professor from Canada. So, well, I mean, looking at, many of your presentations, I was seeing a lot of very long structures. So, but usually what you do is you take some kind of local measures. To extract this, sometimes we call it very long structures. So I have the feeling that these things are more, animals which are actually have global behavior, so some kind of integral behavior. And well, that was the reason why I decided to give a talk on this kind of thing. So, well, this first, helical flows, and we see this kind of helical behavior in many problems in fluid mechanics. I'll just show a couple of pictures in a minute. And we also see that locally in turbulence very often, and then I will show you the mathematical formulation of this helical type of thing. Give you the equations. Then we'll talk a little bit about conservation laws, how to construct them. And I show you some probably new conservation laws for this helical type thing, which are inherently non-local, which I found extremely surprising. Symmetries, I will probably not force you to want with symmetry today. And that's probably not yesterday. Well, that is, just a bunch of pictures here that are taken from various websites. So, we do know that helical structures appear very often. Also, there is this extremely famous paper here of Lundgren here in 1982, where he actually used helical type of structures to cook up somehow the K-Manning spectrum, if I remember that correctly. So let's go to the mathematical formulation. The Euler equation, Navier-Stokes, among others, of course, they have the translation group and have the rotation group. Those who were attending my lecture yesterday, that is, you may remember that symmetries, in fact, actually are linear vector spaces, meaning that you can combine them. They're like vectors which you can linearly combine. So, meaning that you can combine any of these groups, so the translation group and the rotation group, to a new group. And that's in fact what I did here. What I just simply did, I combined the z and the phi, and that's a classical formulation. To formulate a helix, and the helix here is, of course, the new independent variable. So we are kind of restricting now to helical coordinates. Of course, on top of that, of course, we have the radial coordinates. So we start with cylindrical coordinates, r, z, phi, and then we restrict ourselves to this limited set of coordinates. So here that is, sometimes this kind of reductions are called 2.5 dimensional, since we have still three velocities, but apart from that, we only have the r and the psi here, which remember on the previous page is essentially this type of helical coordinate. And of course, we do have time. And it is actually convenient to introduce curved linear velocity vectors that in fact is not necessary, but it makes it just easier to deal with the whole thing. Well, what we can do now is actually compute various things in these helical coordinates. And for example, we can write down the vorticity, which has then a limited form, a reduced form. The psi is in that direction. In that direction here. That is normative to this helix, which is apparently there. There's also some other things here. The omega eta, which is in this kind of direction, which apparently is a non-trivial behavior here. And in fact, we already have introduced here this psi, which in fact is, of course, the string function. Since we only have the psi and the r coordinate, so we have u r and u psi. If you look at the continuity equation, I'm not sure where I have it here. No, unfortunately, I didn't show it. Anyway, what you can do is you can introduce a psi, And also what I haven't written down here is if you write the psi, in terms of the two velocity, it's a non-local quantity. It's a line integral. So it's an inherently non-local quantity. So it's non-local quantity. So if you have u given and you want to compute psi, you have to do it. And at the same time, of course, the velocity here now, in view the total the vector here, of course, is given according to the ER, and then of course according to these coordinates. Now, if we now look at the equations, then we find two or three interesting things here. The first one is this v velocity here that goes in that direction. Here can be rather simplified. Forget about that term. That is a complicated diffusion term here, the viscosity term. And interesting enough, here we can see probably in the next slide that this thing here can be written in a very simple form. And this is the equation for the psi here. This is the equation for the psi. And the actual quantity that is important is this one. So there is this capital psi, that's a function of this one here. So we can write down this one here in this form. Apparently, it doesn't look like a conserved quantity here at this point, or a conservation law. But we see later in a minute that this is in fact the case. So this V eta equation, if you look at the steady and the implicit limit, that's a classical result that is called the JFKO equation. What you can simply do is take this one here, that can easily be integrated in this form here by introducing the string function. So put in the string function here, that can be just integrated by a method of characteristic. So the V eta here is just an arbitrary function of the psi. And at the same time, using that steady and implicit limit here, you can introduce the psi equation. And interesting enough, this psi equation can be integrated one more time, and we get this type of equation, which has, I think, different names. One of them is actually the JFKO equation. So that is an equation that has in literature been investigated quite often, in fact, in various contexts. Sorry. Well, there's limiting cases, of course. The axisymmetric limit here, the plane and axisymmetric limit. The plane limit is simply if A is equal to 0 and B is equal to 1. Remember that. So if A is equal to 0 and B is equal to 1, we just have the R phi coordinate system, so that is the plane one. And if A is equal to 1 and B is equal to 0, that means we have only the RZ coordinate system that is an axis. And these two limited cases are also well known. Of course, that is a well-known equation. I'm not sure if that has a particular name. For plane flows, plane inviscid flows, and for axisymmetric flows, we have this equation that's sometimes called the Brad-Forsson equation, or the Grad-Sheff-Renoff equation. Maybe have more names. So what we saw on the previous slide is, in fact, is a generalization or a combination of those. Well, the equation you have seen so far are essentially not in conserved form, but what we essentially want here is we're searching for fluid dynamic-like conservation laws. So essentially, you have everything here written under gradients. That is a time gradient, and of course, you have spatial gradient. Well, that is probably what is close to Euler and Navier-Stokes. So suppose we have a set of non-conservative differential equations. This type of thing. So identifying what we had in the previous slide. And now what we're looking for is to rewrite this one here in a conserved form. So the general condition for a conservation law, if and only if we find multipliers of this form, and then the whole thing can be written here in terms of this general divergence operator. So what we're really looking for is this type of multipliers here, such that this equation can be written in conserved form. And we do know that, I mean, if you have some conserved quantity, that is extremely helpful for understanding, but also numerically. And actually, we tried that. Well, let me finish that very quick here. Yeah, that is the necessary and sufficient condition to actually define here these multipliers. And this E here, this E UK, that is what we call the Euler operator. I'm not going into detail on that, but there is apparently a regress method. If you have an ODE or PPE, use the whole algorithm here. You can read that here in a bunch of papers by Blum and Anko Triakov, how actually to rigorously derive and conservation. Well, this is just, I mean, forgetting all the calculations. And now what we do see here is a variety of different conservation laws. And, well, this one here apparently is this capital psi depending on this low phase psi here. And this one here apparently is non-local in time. Well, this is essentially a classical one. It's local in space and time. Another one here is also local in space and time. That is this one here. And the last one here, I think, is the most interesting part because it has actually this additional factor of psi. So this type of conservation law is in a sense local in space and time because the psi is a non-local quantity. So at least we haven't seen that before, and we were rather surprised. So that triggered actually the idea of presenting it here, because it's an inherently non-local structure, which might have anything to do with something to do with the structures and turbulence. Well, I'm not. Well, that's probably you skip that. I mean, we're not interested in the symmetry at this point. So what we did, we found new local and non-local conservation laws. I think that's an important part. The symmetry analysis, I mean, in fact, did not show any new symmetries compared to what we saw yesterday. Open questions, do there exist more conservation laws? I would say mostly likely yes. So we may actually explore more conservation laws in fluid mechanics, at least in distance fluid mechanics. And do there exist more symmetries? Well, that I don't know. Maybe not. Okay. Thank you.
Other questions? Where do you think you can make the closest analysis of the fluid mechanics?